I guess I will announce the next talk once more. Dr. Thomas Keutel from Technische University in Chemnitz with his talk on real-time diagnostics on sustainable industrial processes.
So,
stage is yours.
Yeah, thank you very much for this introduction. Good afternoon, and now I hope you have a little bit brain capacitance left. I became a little bit more theoretical now. I apologize a million, the German title, it's the only German line in my presentation. Okay, what is my idea? Real-time diagnostic for sustainable production. We have seen in the presentation before still some items, some keywords, Green Deal and so on, and now it works. And the idea or the mindset is maybe now established that we need to change something, yeah? And we go through the world, we attend conferences, and a lot of people speak about sustainability and improving the CO2 reduction and so on. But we ask always the question, how do you do it in detail, yeah? They spoke about software, they spoke about KI and XY, but which information they use? And then always answer comes, I don't know. And our idea is to look into our capabilities. We are a university in Chemnitz. As it is mentioned, my chef is Professor Kanun. We are dealing in the field of measurement and sensor technology, and we ask ourselves, what can we contribute with our ideas, with our techniques, to improve production processes in the sense of sustainability. A short recap, we have 5 main working groups in our team. We are dealing in almost all aspects which are almost common in the sensor technology. I want to speak about impedance spectroscopy, that's why here no more details. We are developing physical sensors, we are dealing also with wireless sensor systems, we are developing also electrochemical sensors, and if we combine everything, we are in the range of smart wearables. And this is also a little bit the development of our team, and covering information or technology is the impedance spectroscopy, and in all these fields, this measurement technique is more than less involved. And this is also the measurement technique where we have the international workshop on impedance spectroscopy in our house in Chemnitz since nearly 20 years now. This year we have the 18th run of this workshop. Okay, sustainability in manufacturing. I'm sure you are almost common with this background, the sustainable development goals provided from the United Nations. And if we cut it down to the demands or the requirements of companies, we have intrinsic and extrinsic motivations. Yeah? The intrinsic motivations is maybe the scarcity of resources and energy. Yeah, the energy is in the most cases the question. Cost reduction, increasing quality, less rejects. Supply chain problems, circular economy, these are intrinsic motivations for sustainability. Extrinsic ones, I don't want to come to each aspect in detail. I want to highlight the Corporate Sustainable Report Directive, the CRS. This is a demand from the European Commission, which causes in the future, more reporting. Yeah, we have a lot reporting yet, but this is a demand which will come, and in a lot situations, in a lot cases, the companies don't have measures in the hand for this requirement. Focus, CO2 footprint optimization, energy and resource utilization. This is so far the motivation which we were looking for. And the question now is the impedance spectroscopy. how can we contribute to support this process, to generate new or not accessible information in the production process to improve the sustainability at all. And now, I'm sorry, I need a little bit theory. I need to explain a little bit the impedance spectroscopy at all. So I have here now some slides. At the end, I want to make it short. Impedance spectroscopy is something from the field system testing. Yeah? I have an excitation signal. I apply this excitation signal to any kind of a device under test. I got the output. I crunch this both informations, and I have here a curve of any kind of a system, a UI curve. Excitation signal is always, in the most cases in the theory, a sinusoidal signal with a certain frequency. We apply in a working point, we get a response, and the output is at the end in this so-called Nyquist diagram, real part and imaginary part, one frequency point. This one, if I use one frequency. Now we take care of this spectroscopy aspect. We are using multiple frequencies. I have multiple frequencies, I have multiple responses, and at the end I such a characteristic curve, the so-called impedance spectrum, is born in this so-called Nyquist diagram. So to make the story short, this is it's a non-invasive approach. We don't need to destroy devices under test. We can deal in a conductive way. We go with the electrodes directly to the probe. In the case of batteries, we can use also a capacitive coupling. We have two capacitor plates, and we can analyze the capacitive impedance. And we can go also for the inductive one with coils. And this is, in our understanding, the inductive spectroscopy. So we have a huge palette of instruments for a lot of fancy things. Non-invasive, we can resistive, capacitive, or inductive. And what is the strength of the approach? The separation of effects because of the frequency response. Later more. At the end, we're dealing with this approach in a couple of in a couple of different application fields, and I explain it always in that way, that everything what is surrounding us, this material, the air, this floor, or even a technical system has an electrical fingerprint, and this is this particular impedance characteristic. And we develop a method to analyze this fingerprint and to bring it out from the laboratory. Impedance analyzer, maybe some of you are in charge, are costly devices, several 10,000 euros, and it is an approach in the lab. We need to transfer it to an embedded system to get it in a real-time process, in a production process. Okay, separation of effects. Now you see here also a theoretical impedance spectra. It looks like a spectra from a lithium-ion cell, and you see here different branches, and you see also frequency ranges. You see here millihertz and here kilohertz. This is the specific frequency range we need to apply for especially this application, for this battery system. And then separation of effects. We have here the so-called RS point. Not so really important. It is state of the art in the battery diagnosis, but really without any sense. Then you have here the so-called diffusion part. This is this almost linear line, and this is in this frequency range we describe electrochemical characteristics. So you need to understand if we go for millihertz, yeah, there is taking place a certain polarization of the huge molecules in the electrolyte. If you increase the frequency, the heavy weight of the molecule is too huge, and this part is going out of this signal what we measure, and another effect became dominant. And this is exactly this curve. Yeah, the frequency reaches this point, the polarization of the molecules does not take place anymore, and then this curve occurs. This is a so-called electrode 2, the electrode 2, and in these frequency ranges we can characterize the lamination of the electrodes, for example. So, and I don't want to go so deep in detail, but this should illustrate we can choose a frequency range, and we can decide by choosing this frequency which effect we determine. Yeah? And if you go in this range, we can take a look to the electrode 2, to the electrode 1, and here we have a small inductive part which we can use also to measure temperature inside of the battery cell. Okay. All these parts of the curve are well describable, and we call it a physical model, and this is always our understanding. We try to reach a physical model of our device under test. We want to understand what is the reason for this behavior, and this is our most transparent example for this reason. I have here, another German sentences. We have a qualitative and a quantitative analysis. Yeah, and for the qualitative one, we simply evaluate changes in the curve, and this is at the end the most simple approach. We measure the impedance spectra to the time x and the impedance spectra to the time y, and then we take a look, is there any kind of a change without any understanding why? Yeah? The quantitative approach is exactly what you see here. We ask ourselves, what is the reason, or how is the physical or the electrochemical background of exactly this behavior? And then we have a physical model, and with this physical model, we can measure real physical quantities. Yeah? So this is quick and dirty, and here, yeah, we need a lot time effort in our lab. So, and what I was explaining now, you can see here on this slide. Yeah, this is, let me say, our greatest IP of our chair. We ask ourselves, what happened between the electrodes if we make the impedance measurement? And what you can see here, for example, this is the battery again. Yeah, you see here on the x-axis the frequency range from 10⁻⁶ to 10⁻⁹, and here 10⁻⁶ to 10⁻⁹. So this is a range of, let me say, theoretical impedances at all. Yeah, and over the time, over our research, we developed this diagram which physical effects or characteristics taking place in which frequency. And you see here the battery. It is in a low frequency range because the effects, the phenomena are slow. And you know also, if you measure a battery, you speak about ohms, you speak about milliohms. If you go for soil, for example, yeah, you have much higher impedances, almost an isolator. And in that case, we need to increase the frequency. Then we need to go in the kilohertz, megahertz range. Right now, we want to continue with polarization effects in polymers. There we need also the gigahertz range. So, and what can you see here also? The battery in this range, and here, for example, bounded water. I'm sure all of you have a microwave at home. What does a microwave do? Agitation of water molecules. And that's why everything what is anyhow related with water, we agitate in this frequency range. If you speak about humidity in soil, humidity in wood, or whatever, we need as agitation signal exactly this range. So, and this is our methodology. We take a look to the device under test, I had here a talk to a colleague. He wants to know aging process of a sensor. Yeah, so I can't give a number. I can't give a number, but if I understood what is the aging process in detail, which phenomenon is saturation of maybe water in the substrate material, then I can define, okay, to analyze the aging of the sensor, I need the frequency like this. If I have a contribution of an electrolyte or electrochemical system, then I need to go down with the frequency. Yeah, and so this is our development process that we need to take a look to the device under test, to the question which is asked, and then we design exactly the required parameters for our embedded system design. To make it short, impedance spectroscopy is a measurement method in analytic labs. These are huge devices. You need to pay a lot of thousand euros. But our strength, our goal is to bring it in a small electronic system, robust, full automated, and also by limited resources. And how is it possible? We, let me say, it's a process. First of all, for sure, we need to understand the problematic in the lab. Then, in the next step, we take a look for representative frequencies which help us to generate the needed information. And at the end, maybe I need 2 or 3 frequency points which are sufficient to give me this answer. And with this little step, it is possible to reduce the performance from this broad spectra analysis with a lot data, with a lot measurement time, yeah, to a small and tiny system which can be embedded work in a process. We have, in the meanwhile, also some references. We have a company, a project with a company to detect counterfeit coins. And there we were realizing a system integrated in a system, and we can detect 500 coins per minute, also in real time. Okay, here I guess the last theoretical slide. Sorry for that, but it is important to understand what are the needed steps. As I said in the beginning, we need the excitation signal. So we need to design exactly this spectral information. We need to apply it to our device under test. Then we need to measure voltage and current. We need both informations. Yeah, and also here the problematic, we need it in parallel. Because of phase shift, it's not possible to multiplex it, yeah, to measure voltage and current. Yeah. In the worst case, it works, but it's better if you can measure it really in parallel. Yeah, and then we have the impedance determination and at the end the data analysis. Up until this point, it is hardware, and from here it is advanced signal processing. Yeah, okay. Yes, we did it in a lot of different application fields. As I said, here you see our impedance battery lab with a climate chamber and our hardware. We do it also at the human body in bio and biomedical application fields. Only to give you an idea, we are dealing in a lot of different application fields. But now, impedance-based diagnostic in manufacturing processes. So I need to hurry up a little bit. We are dealing since maybe 20 years in this field, impedance spectroscopy. We are developing a lot projects in this field. And some years ago, we asked ourselves where we are and what we want in the future. Such a internal procedure, and we found out that we are dealing with almost all physical domains you need also in a production process. So this is an artificial one, yeah, for sure. here is not a real production process in the background, but what are included? Incoming goods. Yeah, you have always in a production process things which are coming in. You have to deal with liquids. If it is a color, a process water, or a jam, or in the food branch, yeah, whatever, yeah, milk. You have liquids. You have polymers. In a lot of companies, you have to deal with polymers. We have metal forming processes, combination processes, and at the end, you have end-of-line tests. This is so far our classification of typical branches. Yeah, and here it is written down. You need the CSRD. This is a Cooperative Sustainable Reporting Directive. You need to explain, hello, I work on a almost CO2 reduced level. Yeah. So now we go through the steps: raw material, liquids, polymers, metals, and products. And we start here in the incoming goods. Yeah. So sure, we are now a little bit in the future. And in the future, you will have, if you take a look in the research, the question of recycling becomes more and more concrete. I don't want to speak about our automotive branch. They are really in charge of this, because until now, each exported car counts as 100% recycled. I don't speak more. Yeah? They have really an issue now. So recycling become more and more an issue. Also, supply chain. Yeah, you see the problems with Corona. The supply chains doesn't exist. So maybe you need a second or a third supplier for your products. That means tolerances. Until now, you were a company and you say to your supplier, hello, I need this and this raw material and this within this and this tolerances. And if you cannot, then I go to another. So, but if we speak about recycling and maybe recyclation of material, yeah, you can't guarantee anymore this tolerances. Also, if you go for natural products, yeah, we are dealing in our team also with palm fibers, yeah, you don't have anymore such straight tolerances. So you need to deal with. So even in this point in the incoming goods, you need more information. It will come. For controlling reduction of rejects, increase quality, improve availability, sustainability at all. Yeah? So you define in the beginning of your process parameters. Okay, let's go on. Liquids. You have fill levels. You have quality of your of dispersions. You have sedimentation of particles, or you have evaporation processes in a tank or something like that. It's a problem. Until now, difficult to observe. We have here an example. It is still some years ago. It was a PhD in our team. We have here a simple proximity sensor with a capacitive principle. So, and there's a tank with a viscous medium. Yeah. So, and what is the problem? Is this tank it is the real level, or is it a conductive film at the wall? Yeah. With a standard capacitive proximity sensor, you don't get this answer. Yeah. We apply simply a few more frequencies, and we can distinguish between this conductive film and the real medium. Only as an example. I don't want to go more in detail. If you are interested in, we can discuss later. Monitoring of tank level. Further possibilities. We made also liquid quality. We measure in water ion concentration. And for example, dispersion composition. Yeah, maybe someone who knows us. We are developing also polymer sensors. We are dealing CNT dispersions. We characterize our CNT dispersions also with impedance spectroscopy. There are a lot applications and questions which we can solve with the impedance spectroscopy, simply with this multispectral approach. We continue with the polymers. Wow. Characterization of printing process. This is my chosen application for now. Characterization of percolation, material homogeneity. Yeah. So my approach, which I was chosen for this presentation, is a printing process. We have a company in Chemnitz. I'm sorry, I need to accelerate a little bit. They want to print batteries. A printed battery, is a multi-layer system. Yeah. And honestly spoken, I am sure that even with the first layer, you define if this battery became a battery or not. Yeah. Quality. So our idea is, or not our idea, our possibility is to measure each of this production step with a capacitive structure. We measure in our laboratory the so-called golden sample. We have an idle product, and we measure this electrical characteristic from this golden sample. Later on, we can go in the production process, even in this huge matrix with a lot of points, and we compare at the end the impedance spectra with the golden sample. So this is quickly done. This gray curve is at the end a tolerance band around the idle curve, which is maybe acceptable. Yeah? Then we have the second printing step. This is this yellow layer. What do we need? Nothing else. We have, again, our capacitive structure. The only change is in the microcontroller, the model. Other model parameters for the second, for the double layer system. And also here, we have the idle example, the golden sample from our lab, and we compare it with the result. At the end, we have a matrix analysis. We have also approaches for this. And we can generate from this matrix IO, IO, NIO. And maybe here the yellow one, maybe the process parameter should be adjusted, a little bit more heat, a little bit more oxygen, whatever, for the next production step to get it back. Yeah? And state of art is that this complete matrix will be processed from the beginning to the end, and at the end you make an end-of-line test, and you find that you have a lot of waste. So this is, from our understanding, a huge contribution to reduce, to improve the sustainability in printing processes. We continue. Percolation. This is, for example, our approach for polymer sensors. We have a polymer substrate, and inside we mix copper nanotubes. We use also the impedance spectroscopy to characterize this drying process, which you can see here. We can follow this procedure to optimize this procedure. I go further because time is almost done. Metals. For magnetic material, we don't use capacitance. Here we apply the inductive spectroscopy. We use a coil, and we use the so-called eddy current effect, Maxwell-Wagner. And here are questions like deformations, dislocations, densities, microstructure, and mechanical stress. These are parameters which are a lot asked here in this hall. And what are the sensor requirements? Non-contact measurements, real-time data processing, robust, stable for industry use, compact sensor sites, and compensation of influencing factors. Yeah? And what can we do? We have a coil, which, yeah, okay, we need to come 5 millimeters to the system. It can rotate. Yeah, it can be hot. Yeah, and more than 1,000 degrees. And then we can measure our impedance spectrum. Here, quickly, the eddy current. We have a coil. In this coil, we put also our multispectral information. And here, the relevant phenomenon is the so-called skin effect. Yeah, if you have a high frequency, the eddy current is scratching on the top. If you have a low frequency, the eddy current is going deep into the material. And so we can take a look inside of the material without destroying it. So this is our current approach. It's the so-called MST flower. MST, this is our shortcut, and the flower, it's the main coil and some surrounding coils. And with this, we can measure anisotropies, and I want to highlight the permeability of the material. Now we need to ask ourselves which phenomena cause a change in the permeability, like stress, like torque, like grain size, temperature. All these parameters cause a change of permeability, and we can measure it without touching the material, without destroying the material, because of our multispectral approach. Yeah, okay, I can explain the aspects, but I don't have time. Yeah, what is important, if you have a coil, eddy current sensor, we have a so-called tilting phenomenon. If we have a disbalancing of the sensor, because of this multi-coil approach, we are able to compensate such a tilting effect. And something else, we can also measure flux. Yeah? Flux of a magnetic field we can also detect with this sensor. This is an experiment where we detect with our system different material types. Here you see a theoretical model, and here points from real measurements. Yeah, I don't want to come so much in detail, and here you see curves of non-magnetic and magnetic material depending on different frequencies. Okay, so one practical approach. This is a hot rod approach. This is a product which measures the shape of metal in the production process, and this metal is very hot, up to 900 degrees, and the speed of this procedure is also more than 20 or 30 meters per second. Yeah, this is so here, I'm sorry, the right English term is missing, but it is really in a harsh environment, also approach using inductive spectroscopy to detect such errors, which can be used to adjust process parameters to reduce this failure at all. Okay, then end-of-line testing. Okay, it's the last presentation, so I'm so free. End-of-line testing. Here I want to speak about our battery diagnosis. The battery is maybe a product end-of-line production, and here you see a comparison of four cells of the same type. And what did we do? We measure in these SOC stages an impedance spectra. What is the procedure? We charge the battery fully, we discharge to evaluate the complete SOC range. Then we go to each 10%, and then we measure the impedance spectra. And we see here cell 1, 2, and 4 are almost similar, and cell 3, we have a shift, especially here in the 70% SOC. Yeah, you can ask yourself, doesn't matter. Yeah, but if you take a look here, this is the real part. The real part is causing heat losses. That means this cell has the double heat loss than all the partners in the stack, and this can become critical. We have a source for a hotspot, and the hotspot in the battery system is almost critical. Yeah, so this is an end-of-line test for systems, and you know, we are dealing with almost all battery types. Here you see this characteristic curve of a Li-ion. In our understanding, also the lead-acid batteries will have a story in the future as well. Yeah. So in all these models, in all these measurements, you have characteristic elements, and we use this. This is a support system in our university, and in regular manner we go there and make measurements, and here we can play a bit with our methods as well. Okay, so I am at the end. What was my idea? To illustrate a scenario how we can support a sustainable production process in the future by means of using impedance spectroscopy. Here once again this production plant illustrated, and yeah, it is a new approach. We can generate informations inside of a process which does not exist until now, really. So, and this is something which needed to come into the brain of the companies, and that's why I am here. We have a lot different disciplines which we can deal with. We are in the medical branch. We can go with polymers, metal, food, agriculture, and we see a huge potential in this method. And one step is really important, that we reach the level to bring it in an embedded system. And this was really the need to get out of the laboratory. Okay, if you want to know more about this approach, we have in this autumn, oh, this is false, this is not May, this is September. We have always our international workshop on impedance spectroscopy, and you're welcome in Chemnitz. And because of the chronology, we have in 2 weeks, oh my God, the IMTC in Chemnitz. This is also fancy and a lot work. Many thanks for your ear, and I hope you enjoy, and maybe you have a question.
Thank you very much. Also for taking up the time entirely. Since this is the last talk of this session, we can have a question from you if you have one. If not, this is also fine. And thanks a lot also from my side again for your kind attention. I'm closing the session, and I wish you good luck and a lot of success for the rest of the exhibition. Thank you very much.